In this video we'll talk about rigid body work and kinetic energy. So let's do a little bit of review and also learn a few more concepts. Kinetic energy of translation is found by taking 1/2 the mass times velocity squared. Now with a rigid body we also have the potential of the object rotating as well as translating. So the rotational kinetic energy is 1/2 times the mass moment of inertia times the rotational speed squared. So if the object is both translating and rotating, we add those together to determine the total kinetic energy of the moving and rotating object. Now if the object happens to be rotating about a fixed axis O, then we could do a parallel axis shift to O, and this 1/2 I omega squared would be the total kinetic energy, but that's only valid if point O happens to be a fixed axis. Okay, and of course potential energy due to gravity is mgh. Potential energy of a spring is 1/2 ks squared. Work for a linear translation is force times the distance. What about for rotation? Things that are rotating. There's a torque that's placed on it and it rotates a certain angle. The amount of work done on a rotating object is the moment or the torque multiplied by the angle that has been applied through. Okay, so let's see how this affects our energy accounting equation. We have our initial energy. We're going to add or subtract work to give us our final amount of energy. This is just accounting. We're accounting for energy, just like you would in your bank account. And for mechanical systems, we're dealing mostly with kinetic and potential energy and non-conservative work. So kinetic energy, now that we're looking at rigid bodies, would include, of course, the linear kinetic energy, 1/2 mv squared, as well as the rotational kinetic energy, the 1/2 I omega squared. Potential energy could include the gravitational potential as well as spring potential. And the work could be the linear work that's done or the rotational work that's been done. And this is non-conservative work, remember, which would include work of friction, a motor that happened to be applied, or any kind of push or pull that happened. And in the end we could have kinetic energy that again would, because it's a rigid body, could be made up of linear kinetic energy as well as rotational kinetic energy. And we could also have some potential energy left at the end, which would be the gravitational potential as well as any spring potential that's still stored in the end. Is there such thing as negative kinetic energy? No. An object is either moving or it's not. If it's moving, it has kinetic energy. If it's not moving, it has no kinetic energy. So there's no such thing as negative kinetic energy. It just doesn't make sense. What about negative potential energy? Yes, there is such thing as negative potential energy. If something is above a datum, we say it has positive potential energy. If it's below a datum, we'll say it has negative potential energy. Is there such thing as negative work? Yes, there is. If the work is adding energy to the system, that's positive work. If it's taking energy away from the system, we'd call that negative work. So let's put this together and analyze a Cub Scout Pinewood Derby car. There's a ramp. We'll place our car at the top of the ramp. There's 3 or 4 cars placed at the top of the ramp and they're going to race. There's a gate that holds the cars in place, and someone will rotate the gate down, and all 3 or 4 cars will start at the exact same time and they'll race down the ramp. Now if we have an understanding of these energy and work principles, that will help us design a faster car. So here's what's happening. We have potential energy at the top of the hill. The car has potential energy. As it goes down the hill, we're losing some of that energy due to friction from air drag, as well as friction loss in the wheel bearings, as well as some friction loss due to the car wobbling and bouncing as it goes down the track. Once it's at the bottom of the track, there's of course energy absorbed in the rotational kinetic energy of the wheels. And then any energy left after that would go to the linear kinetic energy that results in a faster car. So of course potential energy is good. More potential energy is certainly better. Friction loss is bad because that consumes energy. The rotational kinetic energy in the wheels is also bad. That's an energy consumer. And of course, the more kinetic energy, the more linear kinetic energy we have in the end is better. That means we have a faster car. So to help you understand this concept, I'm actually going to choose some easy numbers. And no, these easy numbers don't really represent actual amounts of energy or a true scale of energy, but at least they'll be easy numbers to help us understand this concept. So let's say I have most of the weight of the car distributed toward the front so that the center of gravity happens to be that high. And let's say that results in 6 joules of energy. And as I go down the ramp, let's say I'm losing about 2 joules of energy in friction effects. And let's say at the bottom of the ramp there's 2 joules of energy that have been absorbed into the rotation of the wheels. Well, if I have 6 joules to start with, 2 have been lost due to friction and 2 have been absorbed by the rotation of the wheels. That only leaves 2 joules of energy left for the actual linear speed of the car. What if I could eliminate friction? If I could eliminate the amount of energy absorbed due to friction, well, then that would increase the amount of energy that's now stored in the wheels and the amount of energy, the linear kinetic energy in the car, and of course the car would go faster. What if I redistributed the weight toward the back of the car? Well, now that's essentially higher and I would have more potential energy. Now let's say we have 8 joules of energy. So if I have 8 joules, that would mean that 4 joules would be absorbed by the rotation of the wheels, and 4 joules would then be available for the linear speed of the car, and I'd have a faster car. What if I removed some mass from the wheels so that they absorb less energy? So instead of 4 joules of energy being absorbed, they only absorb 3 joules. Well, that would allow more energy available for the linear speed of the car at the end, and I'd have a faster car. So let's summarize some of these things we've learned that would help us design a faster car. First, we want to reduce friction effects. We could reduce the bearing friction, and how do we do that? Well, we could put graphite in the hub. The Pinewood Derby wheel is mounted on a nail, and if we put graphite between the nail shaft and the hole in the wheel, that will be slipperier and we'll have less friction. We can also remove the burrs and the crimp marks from under the nail head. The nail head and shaft will have these crimp marks and burrs that if we sand those off, that will reduce friction. We could also align the wheels properly, and that will certainly reduce friction. We don't want to have any positive or negative camber. Camber will either drive the wheel toward the head of the nail or up against the body of the car, creating more friction. We also don't want any toe or steer misalignment. Toe and steer misalignment will also drive the wheel either out against the nail head or up against the body of the car, creating more friction. So proper alignment certainly will reduce friction. We also want to reduce air drag. Air drag is not a really big deal because we're not going at speeds where air drag would be a significant deal, but of course a low profile with rounded edges is certainly best. And we want to increase the weight of the vehicle. We want to make the car as heavy as possible because friction affects light objects much more significantly than heavier objects. The BSA rules allow a maximum weight of 5 ounces. So let's get as close as we can to that weight. Here's maybe something that will show proof that friction really does affect lighter objects more significantly than heavier ones. Let's say I throw both a styrofoam ball and a bowling ball at the same speed. Of course, the styrofoam ball is going to slow down much more quickly because of frictional effects, and the bowling ball won't be affected nearly as much by the frictional effects. So certainly we want to make the car heavier so that friction is less significant. Okay, here's the second item. We of course want to increase potential energy. And we know that potential energy depends on height. So if the center of gravity of the car can be moved toward the back of the car, that will increase its height, and we'd have more potential energy. So weight in the back is much better. I remember watching my sons race their Pinewood Derby cars, and their friend's car was traveling really slow, and he was getting a little discouraged by it. And I noticed that they had put all their weight in the front of the car. And so I whispered to my son, "Tell your friend to race his car backwards." And he thought we were nuts to make that suggestion, but he did it. He turned his car around and raced it backwards, and everybody actually thought he was crazy for doing that. But lo and behold, he started winning races, because if his weight was toward the front of the car and he raced it backwards, that essentially put the weight toward the back of the car. What about making the car taller? Would that help any? At first you may think, oh yeah, a taller car certainly brings the center of gravity higher. But that really doesn't have any improvement, because the car is still tall by the time it gets to the bottom of the track. And so the effective height is still the same. So it really has no improvement at all, making the car taller. All that really does is create more air drag. Now the third item is to decrease the energy absorbed by the rotation of the wheels. So the wheels are going to rotate, and they'll absorb energy, kind of like a flywheel absorbs energy. And we want them to absorb less energy so that more is available for the linear speed of the car. So the amount of energy absorbed by the wheels is 1/2 times the moment of inertia multiplied by the rotational speed squared. 1/2, and the mass moment of inertia is the mass of the wheel times the radius of gyration squared. Now you'll remember that the radius of gyration simply is how the mass is distributed in the wheel. Is it closer to the center or is it further out? And then the rotational speed of the wheel depends on how fast the car is going. It's the velocity of the car divided by the actual radius of the wheel. So if I want to reduce the kinetic energy absorbed into the wheel, the rotation of the wheel, I could certainly reduce the mass of the wheel. I could also reduce the radius of gyration of the wheel. In other words, distribute the weight closer toward the center of the wheel. And I certainly would not want to reduce the actual radius of the wheel, because that's in the denominator. So if I could reduce the weight of the wheels and redistribute the remaining weight toward the center without changing the actual radius of the wheel, that would result in less energy being absorbed by the rotation of the wheels. So how do I go about doing that? Well, this is the standard wheel that comes with the Pinewood Derby kit. If I could cut off those flanges, that would certainly reduce the weight, and as well as redistribute the remaining weight toward the center. And that would result in a wheel that absorbs less kinetic energy, so that more would be available to the linear speed of the car.